Welcome to the Deep Dive. We're the show that digs through stacks of sources to pull out the key insights, basically giving you a shortcut so you're genuinely up to speed. Today, we're diving into, well, a moment that really shook things up. It redefined what we thought AI could even do. Think back to March 2016. Seoul, South Korea, you've got Go, this ancient game, super complex, all about intuition, strategy, millennia of human thought poured into it. And then it meets this new kind of intelligence from DeepMind. An AI called AlphaGo. That moment when AlphaGo beat Lee Sedol, the world champion. It wasn't just, winning a game. It felt huge, like a real turning point. And it's at ripples everywhere, science, tech, even culture.
You've nailed it. Go was seen as like the ultimate mountain to climb for AI for decades. It's way more complex than chess. Deep Blue beat Kasparov in '97, but that was different. Go seemed to need this deep strategic intuition, something that felt really human. Most experts thought, honestly, it would take generations for AI to master Go. The number of possible moves is just staggering, and it relies so much on judging the flow, the feel of the game. People really saw it as a pinnacle of human thinking. So AlphaGo's win, it was genuinely astounding. And yeah, a bit unsettling for a lot of people.
Exactly. And that's what we're doing today. This isn't just a history lesson. We want to really unpack how it happened. We're going to get into the incredible mix of reinforcement learning and neural networks that made the impossible possible. But we're not stopping at the game. We want to explore the bigger picture, how these same methods are now shaking up strategy, optimization, science, even how society works. We'll give you that deep dive, that shortcut to really understanding this huge leap in AI.
Right, so let's get into it. Why Go? What made it such a monster challenge for AI? I mean, we remember Deep Blue and chess. That felt like raw power, right? Evaluating millions of positions a second. Brute force search.
Yeah, Deep Blue was amazing engineering, absolutely.
Yeah.
But it was mostly about massive calculation. Search and evaluate, like you said.
But Go was different. You mentioned the number of moves, astronomical. And the strategy feels so abstract, almost artistic. It seemed like it needed that human feel, something you couldn't just calculate. More about patterns, balance, foresight. Precisely. The complexity difference is hard to overstate. The game tree for Go, the number of possible legal board positions, it's estimated around 10 to the power of 170.
Wow. Okay, that's...
Yeah, it's a number bigger than the estimated atoms in the observable universe. So those early AI methods, exhaustive search, completely impossible, forget it.
Right, you could just throw more computers at it.
No. Go needs really sophisticated pattern recognition. It needs an AI that can look at a complex board, maybe positions that look subtle to a naive view, and understand the deep strategic weight. Human masters talk about an aesthetic sense, a feel for the board's shape, its balance. It guides their moves more than just step-by-step calculation. And that complexity, that seemingly uncomputable intuition, is why everyone thought it would take decades, maybe centuries, for AI, a truly human domain.
And yet, March 2016, DeepMind's AlphaGo versus Lee Sedol, a legend, one of the best Go players ever. The whole world was watching. Man versus machine, but on ground, everyone thought it was still human turf. And the result, just stunning. AlphaGo wins 4 games to 1. But it wasn't just that it won, it was how, right?
Absolutely. The cultural shockwaves were huge, way beyond just the Go world. DeepMind didn't just do the impossible. They did it in this really fascinating, almost alien way. AlphaGo made moves that top human experts looked at and first thought, that's a mistake, a beginner's move. But then later in the game, they'd suddenly see the brilliance, the deep strategy behind it. They started calling them alien moves. It was like AlphaGo had found new principles of Go, stuff humans hadn't discovered in thousands of years. It showed the AI had found paths to victory, strategic ideas that were just outside human conception. So it wasn't just a tech win. It forced this global rethink about AI's potential, how fast it was moving, what intelligence even is. It felt different because it beat us at something we thought was uniquely ours: intuition, creativity, that deep strategic insight.
Truly astounding. But then, hold on, because it gets even crazier. DeepMind brings out AlphaGo Zero. And this version, this is where it gets really interesting, it wasn't trained on human games at all. How did that work? What was the big shift?
Yeah, AlphaGo Zero was a completely different beast. Revolutionary, really, because you're right. It got zero human input about Go strategy, no databases of past games, no expert moves to copy, nothing. Just the absolute basic rules of the game. That's it.
So how did it learn?
Pure self-play. It just played against itself millions and millions and millions of times. It essentially became its own teacher, using a really sophisticated type of reinforcement learning. Now, we'd seen hints of this idea before. TD Gammon, back in the 90s, learned backgammon through self-play and neural nets and got incredibly good without explicit backgammon knowledge. actually beat programs that had it.
Right, I remember hearing about that.
AlphaGo Zero took that core idea and just scaled it up massively, applying it to Go, which is orders of magnitude harder. The key insight was, look, if you learn purely from the rules from scratch, you're not limited by human biases or the way humans have always played. You might discover entirely new, potentially better ways to play, optimal strategies we never dreamed of.
And the speed. The speed was unbelievable. You're saying it went from random moves
Completely random initially.
to beating the original AlphaGo, the one that beat Lee Sedol.
Yeah, the champion beating AlphaGo
Beating it 100 games to 0.
in just 3 days.
3 days, that's almost scary.
It is pretty mind-bending. And then it took only 21 days total for AlphaGo Zero to reach the level of AlphaGo Master. That was the version that later beat 60 top pros online, and the other world champ, Gigi.
Okay, so what does that tell us? That kind of exponential learning curve. Just from self-play, what are the implications?
It implies, well, a fundamental shift in how we think about building intelligence. It shows the incredible power of self-learning when you combine it with enough computing power. AlphaGo Zero didn't just learn Go, it effectively reinvented Go strategy at the highest level. It found principles humans hadn't grasped in centuries. It wasn't mimicking us, it was forging its own, possibly superior intelligence for that specific task. The speed suggests that maybe, for really complex problems, taking human assumptions out of the loop and just letting the AI explore might lead to breakthroughs we can't reach otherwise. It hints that AI might not just solve problems we set, but find entirely new ways to think about them.
Right. So, okay, let's break down the how. If AlphaGo Zero starts from scratch, rules only, and becomes the best ever in days, how does it actually learn? You mentioned this partnership, reinforcement learning and neural networks. Let's start with reinforcement learning, or RL. What exactly is it for our listeners who follow this stuff? How does it enable that self-teaching?
Okay, so reinforcement learning, RL, it's a branch of machine learning, but it's different from, say, supervised learning, where you have labeled examples. RL is about an agent. Think of the AI player learning by doing. It interacts with an environment, which here's the Go board, and the opponent, which is itself in self-play. The agent takes an action, makes a move, the environment changes state, the board updates, and the agent gets a reward or a penalty. Now, the tricky part in the Go, and why RL is key, is that the reward isn't immediate. You don't get points for one good move.
Right, you only know if you won or lost at the very end.
Exactly. It's a sparse and delayed reward. RL algorithms are designed to handle this. They have to figure out which moves, way back at the start of the game, ultimately led to the win much later. It's called the credit assignment problem. The agent's goal is to learn a policy, basically, a strategy, a sequence of actions that maximizes its total reward over the long run, winning the game.
Okay, that makes sense. Learning by trial and error, essentially, but figuring out long-term consequences. So this policy, that's the AI strategy for Go. And how flexible is this whole RL idea?
Yeah, the policy is the core strategy. It's a map. Given the current state of the board, what's the best move to make next? And RL methods are the algorithms that refine this policy through experience, through all those millions of self-play games. The flexibility of the RL framework is one of its biggest strengths. It applies way beyond games. A time step in RL could be milliseconds for a robot arm adjusting its grip, or it could be years for a long-term investment strategy. Actions can be tiny muscle movements or high-level decisions like launch a product. And states can be raw sensor data, like pixels from a camera, or really abstract concepts, like the AI being uncertain about something or surprised. There are various R algorithms, too, like SARSA, which helps an agent make decisions based on Q values. That's like a score for how good an action is in a given state. And then there's this fascinating area called inverse reinforcement learning, IRL. People like Andrew Ng and Stuart Russell worked on this. Instead of giving the AI a reward function and letting it learn a policy, IRL tries to figure out the reward function itself just by watching optimal behavior. So you could potentially teach an AI human values by letting it observe human actions.
Wow, okay. That sounds powerful. So AlphaGo used versions of these RL ideas.
Primarily variations of deep Q learning and policy gradients, yes. But the whole field of RL, including SARSA, IRL, it shows how diverse the approaches are for agents learning optimal behavior in complex situations.
Got it. So RL is the learning engine, figuring out strategy through trial, error, and reward. But what's doing the actual thinking, the pattern recognition? What's the brain, so to speak, that looks at the Go board and actually makes sense of it? That's the neural network part, right?
Exactly. Neural networks are the workhorses here, especially for complex pattern recognition. Think of them as layers of connected units, like artificial neurons. The connections between these neurons have weights, which determine how much influence one neuron has on the next. You feed data in like the go board state, it flows through these layers, gets transformed, and eventually produces an output. Maybe a probability for the best next move, or an evaluation score for the current position.
And how do they learn? How do those weights get set correctly?
That's mostly done through backpropagation. It sounds complicated, but the core idea is simple. The network makes a prediction. You compare it to the actual outcome you wanted, like, did the move sequence lead to a win? You calculate the error, the difference. Then you send that error signal backward through the network. As it goes back, it adjusts the weights on each connection slightly, nudging them in a direction that reduces the error next time. Repeat this millions of times, and the network gets better and better. Crucially, you need activation functions in there, things like sigmoid, or, more often now, ReLU. These add nonlinearity.
Nonlinearity, why is that important?
Because without it, the network could only learn simple straight-line relationships between inputs and outputs. Real-world data, like Go positions, is way more complex than that. Nonlinearity allows the network to learn incredibly complex, curved, nuanced patterns and boundaries. It lets it capture the real subtleties of the game.
Okay, that makes sense. It allows for complexity. And we hear deep learning all the time. The deep part just means lots of layers.
Pretty much. Deep refers to networks with many hidden layers stacked between the input and output. These deep models are powerful because each layer can learn features at a different level of abstraction. Think about image recognition. Early layers might detect simple edges or corners. Middle layers combine those into shapes. Deeper layers combine shapes into objects like faces or cats.
Oh, okay. Hierarchy.
Exactly. This hierarchical feature learning is super effective, but it usually needs huge amounts of data and a lot of computing power to train. And sometimes, yeah, they can be a bit of a black box. It can be hard to pinpoint exactly why a deep network made a particular decision. That's still a big research area.
Yeah, and for something like Go, which is visual spatial, are there special types of neural networks?
Absolutely. For anything with a grid structure like images or a Go board, convolutional neural networks, CNNs, are essential. CNNs are specifically designed to understand spatial relationships. They use filters that slide across the input, looking for local patterns like specific ghost-stone shapes or common formations. Early layers find simple patterns, later layers combine them into more complex strategic concepts, understanding the whole board structure. It's a bit like how our own visual cortex works. And there have been big architectural improvements too, like skip connections in models like ResNet. These create shortcuts for the learning signal, helping information flow better during training, and allowing us to build much, much deeper networks, 50, 100, even more layers, without the signal fading out.
Okay, wow. So putting it all together for AlphaGo, it's this tight combination, this synergy. Reinforcement learning is the trainer, setting up the self-play, providing the reward signals, and the deep neural network, probably a CNN, is the brain, learning to see the board, evaluate positions, and predict good moves based on that RL feedback.
That's the core loop, exactly. The deep neural nets in AlphaGo learned two crucial things via RL. 1. Evaluate board positions. Look at the current state and estimate the probability of winning from there. 2. Predict moves. Given the current state, suggest the most promising next moves. This let AlphaGo develop that almost intuitive feel for Go, like a human master. It wasn't just calculating, it was recognizing patterns, evaluating positional strength. Instead of brute forcing every move, which is impossible, the neural net gave it this higher level understanding of the board. It's like how chess grandmasters don't see individual pieces. They see chunks, structures, strategic motifs. AlphaGo's networks learn to do the Go equivalent. And that synergy RL driving the learning, deep nets providing the pattern recognition and intuition, that's what let it master Go's immense complexity and find those novel winning strategies.
Incredible. So the Go win was the headline, obviously spectacular. But you said the story doesn't end there. These core ideas, RL, deep learning, they're now popping up everywhere, right? Changing how we tackle strategy and optimization in totally different areas.
Absolutely. Reinforcement learning fundamentally is about sequential decision-making. So any problem where you need to make a series of choices to reach a goal. RL is potentially applicable. Think robotics, supply chain logistics, financial trading, controlling complex industrial processes, even optimizing traffic flow. AI agents using RL can learn really sophisticated strategies in these domains, often finding solutions humans hadn't thought of. It even mirrors ideas from game theory, like how simple, effective strategies like tit for tat can emerge naturally from learning. And the optimization techniques used to train these networks, they're now fundamental across AI. Interestingly, while you might think the goal is always the absolute perfect solution of the global minimum, often, modern optimizers are happy finding a local minimum that's good enough, and, crucially, generalizes well to new situations. Robustness over theoretical perfection sometimes. Plus, for getting these models out into the real world, efficiency matters. Techniques like quantization.
Quantization.
Yeah, it's basically reducing the precision of the numbers the network uses, say from 32-bit floats down to 8-bit integers after it's trained. This drastically cuts down memory use and speeds up calculations, making it possible to run powerful AI on phones or smaller devices without needing huge servers.
Okay, so better strategies, more efficient optimization, but it's also driving actual scientific discovery and new applications.
Big time. In medicine, AI is analyzing medical images, finding subtle patterns in scans that might indicate disease earlier than a human radiologist could spot. It's helping parse patient records for insights, suggesting personalized treatments. It's becoming a powerful assistant. In business, you see large language models, LLMs, built on similar deep learning principles. They're automating content creation, helping with legal research, writing documentation, even generating code.
Right, the whole you won't be replaced by AI, but by someone using AI idea.
Yeah. Exactly. It's shifting productivity. And AI can also learn underlying structures in data directly. It can build belief networks to model complex probabilities in fields like climate science or finance, where human experts struggle to capture all the interactions. And we're moving towards multimodal AI, systems that combine different inputs. Think AR glasses using eye tracking and voice commands. You look at something and say, "What's that?" And the AI knows what you're looking at.
Yeah, context awareness.
Precisely. Huge data sets like ImageNet for objects or AudioSet for sounds help train networks to understand this rich, multimodal world, integrating vision, sound, language, making AI more intuitive.
This is fascinating because, as you say, the tech progress exemplified by AlphaGo isn't happening in a vacuum. It's starting to really reshape society. Huge promise, but also significant challenges, right?
Absolutely. Job displacement is a big one. AI is impacting work at all levels. Robotics and manufacturing, yes, but also generative AI doing white-collar tasks, even augmenting high-skill professions. It often automates the prediction part of a job, leaving humans to focus more on judgment, creativity, critical thinking, empathy. But that still means massive shifts in the skills needed and the structure of the economy.
What about solutions? People talk about things like basic income.
Yeah, prominent AI researchers like Yoshua Bengio have suggested UBI, Universal Basic Income, might be a necessary adaptation. He argues for a scientific approach to policy, addressing these practical economic impacts head-on to maintain stability.
And it's not just work, it's education, too.
Definitely. AI tutors offer personalized learning, adapting to each student's pace, using Socratic methods to improve thinking. This could free up teachers for more high-touch interaction, collaboration, mentoring. We're already seeing generative AI raise the bar for student work, especially writing. The focus shifts from basic composition to critical evaluation and creative use of these tools.
Okay, so if we zoom out again, AlphaGo was a moment, but is part of this bigger exponential trend. Where does this trajectory lead? How far can AI go?
Well, the underlying driver is this relentless exponential improvement in the price performance of computation. It's not just Moore's law anymore. It's parallel processing, specialized chips, cloud computing making immense power accessible. This fuels model scaling. We make networks deeper, like VGG or ResNet. We find smarter ways to scale them, like EfficientNet. And we just make them bigger, look at the massive parameter counts in models like GPT-3.
And bigger models sometimes just develop new skills.
Exactly. Emergent capabilities. Things they weren't explicitly trained for, but arise from the sheer scale and complexity. Of course, this needs hardware. Specialized AI accelerators, GPUs, TPUs are crucial for handling the massive computations needed for these huge models. They make it feasible.
And this scaling, this increasing power, it starts to bump up against some really deep philosophical questions, doesn't it? About intelligence itself.
It really does. There's this idea that intelligence isn't necessarily tied to biology, that it could be a software property realized on different hardware like silicon, that you could potentially lift intelligence out of the brain.
Which leads to the singularity, brain-computer interfaces.
That's the kind of future thinkers like Ray Kurzweil envision, merging our brains with AI, expanding our neocortex with virtual layers, potentially multiplying our intelligence millions-fold, a fundamental transformation of humanity.
Wow, heavy stuff. And what about consciousness? Sentience.
That's the ultimate question, perhaps. As AI gets more complex, acts in more sophisticated ways, the question of its inner experience arises. Frameworks like sentience candidature suggest we might need criteria signs to evaluate if an AI warrants moral consideration, similar to how we think about animal welfare. Maybe eventually, society, perhaps through citizens panels, will need to make judgments about how we treat highly advanced AIs based on the evidence of their capabilities and behaviors. It's a profound ethical frontier.
What an absolutely incredible arc. From mastering Go, a game humans played for millennia, to potentially reshaping our economy, our science, even our very definition of intelligence. AlphaGo's win really wasn't just about a machine winning a game. It was like lifting the curtain on a new era, showing what this blend of reinforcement learning and neural nets could truly unlock.
Absolutely. Those core technologies are the engine driving so much innovation now. Strategy, optimization, science, medicine, education, the list keeps growing. And with that power comes huge responsibility, forcing us to confront these major socioeconomic shifts and these really deep ethical questions about intelligence and our future.
Which brings us to the final thought for you, our listeners. As these AI systems get more powerful, more integrated into everything we do, maybe even augmenting our own minds, how do we sear this? How do we ensure these incredible tools don't just optimize for efficiency, but actually reflect and enhance our deepest human values? As this new form of intelligence evolves, what role do you want to play in shaping its purpose?